Okay, so we're going to work through a series of diagonalization problems. And so a matrix 6, -3, -2, 1, all right, can oftentimes be diagonalized, which means that you can write it as a product of some matrix, a diagonal matrix, and the inverse of that matrix. So the key here is finding that a matrix, and fortunately for us, that's actually what's built into the Eig function. If you make it P D, which like before we were using V, but P really is probably correct here. You can take that as the Eig of A, and that P matrix that you get there. So in this case, in problem 1, the P matrix is 0.94817, 0.4472, negative 0.3162, and 0.8944. So here's what I want to demonstrate. Take the inverse of P, multiply that by A, and multiply that by P. And what you'll see is you actually get that D matrix. So what we just did is we used that P to diagonalize A. So the trick here is that the matrix of eigenvectors will give you the diagonalized matrix. Okay, so there's a bit of a correlation between these two. So for problem 2, it's just as simple as punching in 2, 2, 3, 0, 3, -2, 0, -1, 2, right? And then taking P, D equal Eig A, and then you get the D matrix there, the P matrix there. And again, if I were to do that, you'll see that the diagonalized matrix here of eigenvalues is the same as inverse PAP. All right, so number 3, similar process. 1, 2, -2, -2, 5, -2, -6, 6, -3, right? So PD is Eig A, and there you go. There's the P matrix and the D matrix with the 3 eigenvalues. I think we have one more of those. So let's do 4. So you have A is 1, 0, 0, 1, 2, 1, 1, 0, 2. Okay. And then we go P, D is equal to Eig A, and we get back the P matrix that we need and the D matrix that would result from doing the diagonalization. All right, so this is a form of decomposition that reveals the eigenvectors and eigenvalues of a particular matrix. All right, so let's look at 5. 5 is a little bit of a different question. Okay, so in number 5, they give us this matrix A, right? And if you take Eig A with MATLAB, it's going to give you 0, 3, 0, 3. So this thing has 2 eigenvalues. Lambda 1 is 0, and lambda 2 is 3. Now, what this problem needs us to do is to investigate both of those eigenvalues. So let's investigate lambda equals 0 first. If I do that, then I have a situation where this matrix 1, 0, -1, 1, 0, 1, 0, 1, -2, 0, 2, -2, 0, 2, 0, 2, times this x vector, x1, x2, x3, x4, is going to give us back the 0 vector. Why do I know this? Because if this is an eigenvalue, then ax should be 0x and 0x is the 0 vector. All right, so this basically tells me that x1 minus x3 plus x4 is 0, x2 plus x4 is 0, negative 2x1 plus 2x3 minus 2x4 is 0, and 2x2 plus 2x4 is 0. So we can solve that system by using Gauss-Jordan. This is literally solving the homogeneous system of equations, and we end up with this, which can be interpreted as x1 minus x3 plus x4 is 0. X2 plus x4 is 0. Okay. So if I look at that and I make x3 equal to t and x4 equal to s, this means that x1 is t minus s and x2 would be negative s. So any solution has to be of the form of t times 1, 0, 1, 0, and s times negative 1, negative 1, 0, 1. All right, so these are linearly independent eigenvectors, and if you kind of think about this, t times 1, 0, 1, 0 is going to give you one eigenvector, s times the other one is going to give me the other linearly independent eigenvector. So I get two of them, two eigenvectors. Okay, so let's look at lambda equals 3. So let's pause this. All right, so if lambda is 3, and that means that ax is equal to 3x, then I want a, which is 1, 0, negative 1, 1, 0, 1, 0, 1, negative 2, 0, 2, negative 2, 0, 2, 0, 2, times x1, x2, x3, x4 to equal 3x1, 3x2, 3x3, 3x4. Okay, so this can be looked at as like x1 minus x3 plus x4 is equal to 3x1. x2 plus x4 is equal to 3x2. Negative 2x1 plus 2x3 minus 2x4 is equal to 3x3. And 2x2 plus 2x4 is equal to 3x4. All right, so that in standard form becomes negative 2x1 minus x3 plus x4 is 0. Negative 2x2 plus x4 is 0. Negative 2x1 minus x3 plus 2x4 is 0. 2x2 minus x4 is 0. All right, so we put that into an augmented matrix, which is going to be, all right, so it's negative 2, 0, negative 1, 1, 0, 0, negative 2, 0, 2, 0, negative 2, 0, negative 1, negative 2, 0, 0, 2, 0, negative 1, 0. All right, so we apply Gauss-Jordan to that, and that's going to give me 1, 0, negative a half, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. So you can read this as x1 minus half x3 is 0, x2 is 0, x4 is 0. So if we let the x3 be t, then x1 has to be half t, x2 has to be 0, and x4 has to be 0. So anything in the form of t negative 1/2, or sorry, positive 1/2, right? 1/2, 0, 1, 0 will be an eigenvector. The problem here is that when we did lambda for 0, we got 2 eigenvectors. And when we did lambda for 3, we got 3 eigenvectors. In order for this to be diagonalizable, I need 4, because it's a 4 by 4 matrix. I don't have 4 linearly independent eigenvectors. So this means that A is not diagonalizable. And you can play around with that with MATLAB and see what happens there. But that's how number 5 works. By proving that it doesn't have a full set of linear independent eigenvectors, we have proven that it is not diagonalizable. Okay, so problem number 6 says that B is equal to P inverse AP, and that B is the diagonal form of A, and we need to prove that A to the K is equal to P, B to the K, P inverse, where K is a positive integer. So this is what we call a proof by induction. The first thing we're going to do is that we need to prove that this is true for K is equal to 1. We're given that B is equal to P inverse AP. So that means that P times B has to be equal to AP. I'm just going to commute that.
Mommy, I need my 100 chart.
Which means that if I take the inverse of P on both sides, I get A is equal to P times B times P inverse, which means that I am good for K equals 1. So the next thing I'm going to do is assume that it's true for K is equal to some number n. So we're going to assume that A to the n is equal to P times B to the n times P inverse. Okay, so we're going to use that fact to prove that this works for K is equal to n plus 1, right? So if A to the n is equal to P, B, n, P inverse, then A to the n plus 1 is equal to P, B, n, P inverse times A, which is P, B, P inverse. Okay, if I take off the parentheses here, I get P, B to the n, P inverse, P, B, P inverse. This is the same as the identity, so this is going to be P, B to the n, B, P inverse. B times B to the n is B to the n plus 1, P inverse. So this works for n plus 1. So if I have it true for K is equal to 1, and I have it true that n gets me to n plus 1, then I have it true for all K. So this is a proof by induction. Take a minute to think through the implications of that, but this is a solid proof that shows it for all K. Okay, so problem 7 says that we want to prove that if A is similar to B, then the determinant of A has to be equal to the determinant of B. So we're going to start with A similar to B. Okay, so this implies that there exists a P such that A is equal to P inverse B, P. So if I take the determinant of both sides here, the nice thing is that the determinant of a product is the product of the determinants. So this can be commuted because these are real numbers. And again, the product of the determinants is equal to the determinant of the product. So this is the determinant of the identity. The determinant of the identity is 1. So we now have that the determinant of A has to be equal to the determinant of B. Part 8 says, does this statement go the other way? Can we show that if the determinants are equal, then the matrices are similar? And the answer here is, quite frankly, no. So this is 7. Let's look at 8. We need one counterexample here. So we're going to let A be the 0 matrix. We're going to let B be the matrix 1, 0, 0, 0. Without a whole lot of work, you can demonstrate that the determinant of A is equal to the determinant of B is equal to 0. However, the only eigenvalue of A would be 0. B has eigenvalues lambda 1 equals 0 and lambda 2 equals 1, because we can read that from a diagonal matrix, right? If they don't have the same set of eigenvalues, then they are not similar, because that's an if and only if statement. Matrices are similar if and only if they have the same set of eigenvalues. So we've just proven that these two matrices have the same determinant, but do not have the same eigenvalues. Therefore, two matrices can have equivalent determinants, but are not similar. All right, so there we go. That's all the stuff on diagonalization. That is the last set of problems for the year. All right, so happy seeing you, dumb. All right, let's move forward.